Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'll not take too much of your time. I'll quickly get on to the agenda. What we have to start with is a quick opening session by Phanindra from ISC. And I'll ask Yogesh Simhan, who's one of the program committee members for summer school, to invite Phanindra.
Good morning all. I'm Yogesh Simhan from the CDS department, and you'll be hearing and seeing more of me today, later on today, and through the rest of the summer school. So I'd like to start off by, first of all, welcoming you all to the summer school, to IISc and to CDS. And I'm going to invite Phanindra Yalavarthi, who's the chair of the Department of Computational and Data Sciences, and he's also a faculty who's heading the medical imaging group over here, to come and talk to you a little bit about our department. And we are really excited to be having this summer school. And you might also get to know a little bit about the kind of research that's going on over here as a precursor to the rest of the summer school. So, Phani?
Okay. Let me welcome you all to this Department of Computational and Data Sciences. And I'll give a quick overview of the CDS. Before I do that, I just wanted to acknowledge the Microsoft Research India, which has put up the summer school here. And it happens to be that this is the first time we are organizing as a new department the summer school. Earlier, summer schools have been organized in coordination with CSA and ECE, but we are a new kid in the block, so we are very glad to do this. Once again, I would like to thank IISc. I would like to thank Yogesh, who has put a lot of effort into making this summer school come to our department and as well as do all the things, as well as all of you. At least in this part of Bangalore, we get up late. I know 9:30 for IISc is early. So generally, IISc gets up at 10, right? So I'm sure all of you have come with great enthusiasm. I would like to thank you all for that. Once again, it is also early for us. So if it so happens that I sound a little bit sleepy, please excuse me. Again, I would like to thank all the staff of CDS who have put up a lot of effort into making you good accommodation as well as taking care of all the arrangements. They will be around here. So at any time you have any queries, anything you want to know about the department, or you want to see around the department, or you want to know anything, please feel free to ask any of the staff. So having said that, I'll start off on my introduction to the CDS. So the Computational and Data Sciences is a part of the interdisciplinary research division of IISc. If you see IISc structure, the organization as such has about 6 divisions. And the interdisciplinary research division is one of the new divisions which is out there, which is part of the new initiative of IISc embracing the interdisciplinary nature of the work. I'm sure Internet of Things is one of that interdisciplinary nature. And we are part of that division. And we are one of the 2 departments which is a full-fledged department. Actually, we are the only department which is under the interdisciplinary division. So that means that rest of them are more like a center in nature. They are like virtual programs. They do quite a bit of services kind of a thing. We are a full-fledged academic department which offers academic degrees, which have academic faculty full-fledged. And we are just formed in December 7, 2015. So we are barely 6 months into existence. So now you can see some of the new faces, some of the new things that is going on. And again, where we were earlier, we were all part of academic wing of the SERC, which is the building which you are in. So SERC also has a lot of facilities, including the Cray supercomputer which you are seeing. They offer supercomputing services to the institute. So the facilities has been separated out. We became the academic department, and I currently chair that academic part. And obviously, we come under the Faculty of Engineering. So if you look at IISc, the award of the degrees doesn't have any departments. Either it is awarded in Faculty of Sciences or Faculty of Engineering. So in some sense, we are, it's good and bad because no department is there. So you can claim that you are part of any other department which is out there or which is doing good. So anyway, we come under the Faculty of Engineering just to make sure. And we offer mainly 3 programs. One is a PhD, which is a doctoral program in engineering. Another one is M.Tech research. Earlier it was called as MSc engineering. Again, it's a master's program with thesis. So there is a rigorous thesis which gets done part of the M.Tech research. we also offer an interdisciplinary M.Tech by coursework, which is in computational science. I'll go over it a little bit as we go along. Currently, if you look at the faculty strength of CDS, we have about 4 professors, 6 associate professors, and 5 assistant professors. And by institute standard, we are fairly large department. 16 faculty members is a fairly large department. Average faculty strength of each department is about 12. So, and students-wise, M.Tech Computational Science, as I told you, has about 26 students, including first year and second year. And we have Masters by Research, which is M.Tech Research, is about 18. PhD, we have about 24. And we do get quite a bit of funding from the government, obviously from MHRD, as well as all government funding sources, including DST, DIT, DBT, CSAR. And then obviously we also receive quite a bit of funding from the MNCs. A lot of the faculty members do consultancy for a lot of these, including Microsoft Research, IBM, Google, Yahoo, Boeing, TCS, AMD, Intel, you name it. We have faculty who are consulting for that. And fortunately, we are the only department which offers admissions in 2 separate streams. So every department in the IISc offers admissions under its department stream, but we are the only department which has 2 streams which offers admissions as 2 separate entities. So one is, we call it as computer systems, which data sciences come under. Another one is a computational science, which is traditionally the computational mathematics oriented ones. And obviously all the students at CDSs are happy people, so you can find them around here, right? And then if you happen to see them, please do talk to them. And then if you want interested in more about the programs, more about why they are happy here, please do talk to them, right? So having said that, I'll just get into the little bit of details about what happens in each of the programs, such that I'm hoping that at least I'll inspire 1 or 2 of you to be the students here. So the M.Tech Computational Science is a unique program. It has been around for 10 years. And it is a combination of both computer science and applied mathematics and numerical methods, and as well as one of the science disciplines, we call it as. And it is truly interdisciplinary in nature, because we are combining the numerical methods or numerical techniques or computational mathematics with the application of the high performance computing, or in a traditional computer science kind of computer systems areas. And then people get trained, the students get trained in this program, and they go through rigorous coursework. By the way, you can see all the way from numerical linear algebra to all the way till high performance computing, data analysis, visualization. So they get trained truly to be the computational experts. So the computing experts, which we call it as. And again, they have to go through a rigorous eligibility criteria, as well as the admission test, come interview. We do this. So they have to have a valid gate score. We take people from all BE, BTech disciplines, as well as all Masters of Science disciplines. In fact, this is the first year, as far as I remember, we have just admitted an MSc Chemistry for this program. So you can imagine the versatility of the program. So we expect people to be good in their discipline, have a little bit play towards mathematics and programming, and then we would welcome them. We don't expect them to have a particular background, but we would expect them to have a little bit play towards computing in general. And again, we conduct a written test. We have an interview. It goes for about a 2 days period, and then not the interview, but the written test is on the first day. The interview happens to be on the second day. And essentially, they get through this program. And by the way, in terms of acceptance, I don't think many of you realize this. We are one of the few departments in the IISc which has very high acceptance rates. So for example, just to give a number, we have about 12 seats, where we have offered to about 17 people, and 12 of them have accepted. In generally, the acceptance rate for the M.Tech program in general for IISc is about 60%. So we are well above the cutoff. So our program is considered one of the very good programs which is doing well in terms of IISc standards. And again, they get good placements. I have never heard in my past 8 years of being here that some student not being placed. So again, so they get placed in very good MNCs, including Google, IBM, Yahoo. They also go to financial firms like McKinsey, Boston Consulting Group to do some financial consultancy as well. And obviously, there are a few students, which has been the recent trend, who are very much interested in doing further studies, either at our department or going into some top-tier universities abroad. So either way, so people do have a good flair for that, and that is turning out to be about 50% of the students currently are aiming for doing a PhD either in the institute or outside. This year has been exceptionally very good year for the PhD program of the department, because 5 of our own M.Tech computational science students have become PhD students here. So which is a very good sign. And again, I told you that in the research admissions we have 2 streams. One we call it as computational science, another one we call it as computer systems. Again, computational science has the same interdisciplinary nature. Computer system is more towards computer systems kind of related areas. And they essentially take electrical sciences, including computer science, computer engineering, information technology people, whereas computational science doesn't expect you to be only from electrical sciences, but they will take everybody who is having a good amount of domain knowledge. Again, computer systems expects you to have a good amount of programming background, and so this is the in the computational science we expect that both math and programming is good. Again, this is for the PhD and M.Tech research, and if you are interested in really knowing about the program or getting to know what kind of things gets happen, hopefully we are going to have in the after 2 days some kind of a poster session by our own students by each lab, so that you can get to know more about what kind of research goes on in this department. Again, we do have a rigorous screening program, so we got to do some initial screening based on gate score, and then we have some written component plus interview. Just to give numbers there, not to brag about our own department. Currently, the M.Tech computational science, we have selected about 17, as I told you. That is out of 1,200 applications we received. And for research, we are not yet got the number of seats exactly fixed, but roughly the numbers I can tell you that we have out of about 800 people, we have selected about 14 of them. So you can imagine that the selection ratio is really small. And then it so happens that you have to be really tuned towards it. And as I told you, it's a good time for you, because anyway you are going to be here for the next 5 days or so. So please do interact with the faculty, please do interact with the labs, get to know if you are interested in the department. And as I told you, because we are a new kid in the block, we do have quite a bit of exciting things to offer to the students. Again, just talking about research students, unfortunately Microsoft stopped the PhD fellowship, but when it was offering, the Microsoft, TCS, IBM PhD fellowships were won by our students. And we received even international fellowships, including SPIE kind of things. And again, I don't want to go into this, but there are numerous best paper awards. There are numerous travel awards which the students of research students of CDS have received. Won many challenges. Again, I don't want to list, I'll just list the recent one, which is the GE Edison Challenge. And again, after graduation, they also won prestigious fellowships like Humboldt fellowships, which is offered in Germany. Again, just to talk about one challenge, this is the GE Edison Challenge. This is about 350 teams have participated in this challenge. That is mainly about smart things and smart city. So, and the person who is closing his eyes with a French beard is our student. So he doesn't like publicity like us. So anyway, so this the team what has done is that they said Bangalore is really bad for traffic. So how to solve this problem? So how to make Bangalore more smarter such that we can operate the traffic signals better, and then make sure that the traffic goes smoothly. And in fact, out of the 350 teams, they have been the runner-up, and including the winner come runner-up, they receive about 25 lakh rupees to implement this in real time, and then see what happens in the next 3 years. And that's a huge thing for the if you are a student, you are receiving your own grant. That is also from a private agency which has no strings attached. I think it's a good thing, and especially I would like to thank the faculty and as well as the students who are doing tremendous job with this. Again, as I told you, there is going to be some poster session where you can really see what's happening in the CDS. But just to give an overview, as I told you, we have computer systems and computational science. We have various things that goes on, starting from CAD for VLSI, a traditional computer science discipline like computer architecture. Then again, we have like cloud and distributed computing, machine learning, database systems. On the computational science, we have medical imaging, scientific computing. So you name it, we are a mini IISc inside our department. So right, we all the faculty work on really diverse areas and really interesting problems as such. So with that, I will stop. I think I have taken slightly over my time. I was given only about 8 minutes, so I took 10 minutes. Sorry for that. But again, I would like to welcome you all. I hope you'll have a fruitful and as well as productive summer school here and learn something new. And I wish to thank you all. Thank you very much.
Good morning. Everyone can hear me? Happy to be here. Primarily, two of us are going to make your next 6 days worthwhile. Many of you have come from far away, and most all of the speakers are spending their personal time to come and share their experience and passion for this area with you. So it's very important that we take the best out of this, and that's the reason why we said it'll take some time to give the context of the workshop and for you to navigate all of the activities that are going to happen in the next 6 days, make the best of the workshop. Okay, so the content, it's all with you. You will see a whole set of lectures, guest talks, panel discussions, hackathon. Slight semantics, lectures are more in-depth where it's supposed to go from the fundamentals about a particular area. Guest talks are by speakers who are solving a problem today, and they are sharing an overview of how and why they are solving the problem that they are. Hackathon is your hands-on session culminating with a project demo. And we also will have panel discussions, which is not the usual thing where the people on the stage keep talking. It is to get you an additional opportunity to interact more with the speakers of the day. Okay? Because the speakers have fixed time slots and the question time may run over. And at the end of each day, you will get to meet them again, ask your questions, clarifications, and so on. That's the intent of the panel discussion. We'll also have Professor Anurag Kumar, Director of the Institute, giving you a keynote tomorrow. He's also extremely excited about this area, and he has extremely busy schedule, but he said, I want to give a full 45-minute talk. Okay? We said, please come and inaugurate and go away. He said, no, I'm not going away. I want to share my expertise with this workshop. So, many speakers from diverse places, researchers in industry, academics, entrepreneurs are going to be with you in the next 6 days, but this unites all of them. IoT for QOL. Any guesses? Perfect. You will find that that's the reason that drives people to do what they do. And I want to spend a few minutes as to what is this quality of life and how IoT can presumably improve the quality of life. I think that's hopefully understood. World is around us. When I say improve the quality of life, there are people who want to have things better. The world is a crazy place, so are humans. World is analog. And before I can make a change to the world, I need to measure the world. I need to see what is there before I can transform the world the way I want. So essentially, I need sensors which read in analog, and we are happier to deal with the digital. So you need to add on with each of these sensors a bit of electronics and a bit of processing that takes this analog values, converts and does some cleaning up if necessary, and sends it up to through some way, some connectivity, because what we want to measure may be far away from where we are trying to decide things with, and I need to send that across through some network infrastructure, collect this data, have some applications and models which use this data, and in which humans decide what you want out of this, and send it back digitally, which then again use some electronics and processing to convert into analog, because the real world is analog. I need to have actuators which work with the real world. Take a simple example, air conditioner. Humans say 23 degrees is what I like. So you probably have a thermal sensor, temperature sensor somewhere, which converts that into some digital. In this case, the 23 degrees is probably set with some infrared remote. Okay? So the network infrastructure, the big name is for using an infrared to set the temperature that I want. And the computation, the data infrastructure, all of that is some kutty thing sitting there which takes the value from the sensor and the number from your infrared, and if it is one way or the other, starts actuating the pump of the air conditioner to cool the place, right? Nothing really new about this. And why would you jump up and down and talk about this IoT. Such a solution has existed for how long? Probably 5,000 years ago. The Pharaoh, finding himself too hot, said, 15 slaves come here, blow till I feel cool. And if I feel hot, I'm going to kill off 2 of you and get 5 more people, right? All of it analog, but the essence is the same. Comfort, whatever I have, I will use to improve my comfort. So nothing here is new. What makes it exciting and why we are having a workshop is the sheer scale of things. IoT is Internet of Things. The scale is that of the Internet. What happens when I have millions of these sensors from all over the world coming together with complex things, which what human life has become today, and how do I take decisions and send it back to maybe thousands of actuators to make the change that I want. This is really the reason why we believe in a cusp of something dramatic that's going to happen, and IoT is everywhere. If you read the business news, you will see it's already there, but it's far from it. Usually hype precedes actual deployment and scale. Sometimes the actual deployment may not happen, but the business news goes on to hype the next thing. Okay? But most of us feel that really there is something dramatic that is going to change, and that's the reason why this whole workshop is set up, because we brought together a lot of people who are working on various aspects of it and want to share it with a new generation of people who will then become researchers in this field. Okay, that's the reason for this workshop. What I want you to do is, as we go through this workshop, it's a huge area, as you can imagine. If you look at, you can actually run, maybe CDS will start M.Tech in IoT, maybe 2 years from now. It's such a large interdisciplinary field that in 6 days, you'll just have a sample. So it's very important for you to put whatever lecture or the talks that you're going through in the context of this big picture. Where is this fitting? Why is this talk in this workshop? What aspect of it is not covered, which I need to look at? So it is not, it's called a workshop, a summer school, because it is not a seminar where you come and listen to people and go away. You have to be actively involved in extracting value. And important notion that you have to remember is this levels of abstraction. Engineering and computer science in particular has made such huge strides because we abstract things out, because otherwise it's extremely complex. So you take a topic in this big picture. For example, the first lecture after the tea break is going to be by Shaz. He's going to talk about something called a programming language P. Okay, so we have presumably come from A all the way, now we are at P. The idea of that language, programming language, is the highest level of abstraction we can think about. Why do we need it? If you have 3 sensors, one here, one there, I can ask somebody, wire it up, connect it up, repair. If I have 100,000 sensors, I need to be able to model it, I need to be able to specify it, I need to be able to verify that this thing does what it is supposed to do. Formally prove that this thing is safe. Formally declare that I am building this complex system which consists of thousands of asynchronous entities, hundreds of services. There is concurrency at scale. There's no way you can use the traditional C, C#, etc. and say, I'm going to build a system. You can build a prototype and say, yeah, I've done it. But when you put a system of this scale out in the world, it's like the medical dictum. Please don't do harm, right? First. You can do good things later. But to convince ourselves that the system is not going to do harm, it's not enough to show 3 pieces and saying this works, I run it for 24 hours, no problem. What about 10,000 of them? There's no way you can run 10,000 of them for 24 days and then conclude. You need to have started with a model, that's where this word cyber physical system comes up, right? Physical things, analog. Cyber is digital. We're combining them. The world, you can model them with partial differential equations of complexity. But you're computing in the discrete world. and the scale. How do I model this, argue about it, and then program it so that I can then deploy large systems like I am going to deploy programs in today. Say 50 years ago, writing a single program was a task. Then we are talking about 5 processors, 10 processors. Then you're talking about multi-core, 300 core, 500 core. How do I efficiently extract parallelism from this? Now we're talking about systems of hundreds of thousands of end devices which are autonomous, asynchronous, and mostly concurrent. So you need a new paradigm. So if you go to this talk, when you start after T, what is this programming language talk doing here? And with this aspect, I'm sure Shaz will clarify this, but I want at every lecture, look at this and say, where is this fitting in? Another example, if you go, I think Ranveer is going to talk about network infrastructure. From this set of devices, I have, what are the options for me to connect to the next level? What kind of technologies exist today? Which is good for what? Cost, performance, battery life, maintainability, all of that will be digging into this particular block in this diagram. Your hands-on is going to, I think Yogesh will take you some more details about why there is a hands-on. You will go all the way from connecting one sensor to one Raspberry Pi, making it work, all the way to thinking about cloud-based Hadoop program which will manage all this data from 10,000 sensors. You need to experience all of that. So we are greedy. We want to compress all of this in 6 days. And it is possible to do so, provided you have this, that I'm going to be on the ball. Many other speakers are going to talk about not particular blocks, but their attempt at taking IoT to solve a real problem, to improve the quality of life. Okay? There is Zainul, maybe tomorrow, day after, who is going to talk about healthcare, in particular ECG. How do I deliver accurate ECG reading to people anywhere in the country within 5 minutes? Assuming there is an ECG machine there. We haven't come remote diagnosis across the country. Assuming there is an ECG machine in Chhattisgarh, no doctors in the neighborhood, I want a doctor in Bangalore, correctly diagnose, send a diagnosis to the patient within 5 minutes. Huge task. It has algorithms, it has machine learning, it has huge data, connectivity, lot of societal issues. Medical care. So they have a startup which is attempting to do just this. So he's going to take you through that journey, but on the background you think about, has he solved this problem? What has he done for this? How do you know this is going to work? These are the questions you have to ask. And this hopefully will be the framework. I'll give you one more example. There is a lot of work on, everybody complains about pollution in Bangalore. Pollution is a huge problem in Delhi, everywhere, on all the major cities. And everybody thinks, okay, if I can sense pollution effectively, then at least I have data to tell people that we have to take action. So there is a company called India Spend, which is trying to do just this. Collect pollution data, present it to the decision makers that, hey, here is a real problem, and by the way, this is where most of the pollution happens, this is the source of the pollution, and can we do something about it? All right? So each of this is designed with one, the scope of the vision that these people have, the problem that they are trying to solve, and their interest and passion in sharing it with you. Okay? So I would recommend that you be alive, active. So I'll just, this is what I want to emphasize, that it's up to you, because all of you are here because you want to learn. And learning happens where you ask questions, and I keep saying, the stupider your question is, the better. Okay? If it's a smart question, everybody knows you are smart probably, but nothing else. You have not learned anything yourself. The stupidest question gives you maximum learning, not for yourself. All those people around you are afraid to ask that question. Right? So strongly encourage you. This is not your regular class. This is an opportunity that you will not get very early and easily. Maximize it. But what we will not cover specifically are huge issues by themselves. Security of all aspects, security of the data, security of people who are going to be controlled or impacted by the systems that you put in place. Privacy is another extremely large issue. Okay? Civil liberties, that's again a much bigger thing. If I know what everybody is doing all the time, can government misuse it to spy on you, to have big data help Big Brother watch you? Obviously, this week is not for those questions, but you should keep that in mind. We are talking about IoT for QoL. Quality of life includes all of these, but by necessity, we will not be able to spend time, but should not stop you asking questions to the speakers about these if you think that's relevant to the talk. Okay? Similarly, the environmental impact, in particular, disposing of electronics is a huge problem. Now, if you're going to spray 10,000 sensors on a field, and if half of them don't work, you can spray another 5,000 if you have the money, but what happens to the 5,000 which is sitting in the field? Who is going to collect them back? Who is going to dispose them off? These are huge problems. Batteries are going to be the biggest challenge in IoT at scale. One, of just recharging. I mean, imagine recharging 10,000 units across 10,000 acres. Who is going to do that? But more importantly, batteries run out of life very soon, and they become poisonous. Who is going to get them out? Who is going to dispose of them properly? In a small network building, it's not a small, it's the largest network building in the department, making sure every machine is connected, up and running the right piece of software is a task. You have system administrators to do it. But if you're going to have so many internet connected devices spread all over, who is going to maintain, update, run software? That's a different question which you've not even talked about. Okay? Because these are large scale system things. Sustainability is the other question. So most of the talks will be about speakers sharing their experience, but you need to keep this in mind, and I hope you get the best out of this in the next 6 days. Okay? I request Yogesh to talk about the hands-on session and put the rest of the session in context. Okay? Thank you. All the best.
So I'll start off from where Manohar left off, right? So this is sort of the big picture architecture you had a look at. So you start with communication, sensing of the environment around you, networking and communication to get the data out from the sensor to some place where it can be collected and processed. And since we are looking at large-scale data sets from large-scale IoT deployments, you have to think about big data platforms for processing these. And finally, analytics and decision-making that actually drive applications and potentially drive actuation all the way back to your entire environment, right? Another way of looking at it, and this is something I feel is intrinsic to IoT, is that one of closing the loop, right? So IoT is only as useful as your ability to observe and also do something based on your observation, right? So this is more of a functional view that I have, where you essentially observe the system, you orient so that you understand what the observations really mean, so you put it in context, and you take decisions based on that using both the current data you get as well as maybe historic data that you have, and then you take an action, right, that you apply back onto the system, and then you repeat the whole thing all over again. And again, this OODA loop, it's been around for decades. It's originally came out in the context of military strategies and so on, but it very well applies to not just IoT, but pretty much everything that we do as human beings also. So if you see something, you actually take it in, you process, you sort of set it in context, and then you take an action based on that. And to me, most interesting IoT applications do follow this kind of sort of loop. So effectively, you're trying to apply this loop on top of the architecture that you have. And in some senses, the IoT stack or the IoT fabric helps you connect the functional requirements along with the architectural capabilities that you have along the various layers of abstraction, right? And one of the usefulness of thinking about it as a stack rather than as a custom application that you're building for a specific domain is that it makes the whole stack reusable, right? So if you take something like, pretty much take, just your networking stack, right? So you have your standard 5-layer stack out there, and everyone sort of uses that. It's not sort of specific to a particular application. So you could go ahead and invent your own networking protocols and so on, but you don't want to do that, right? Because you sort of want to reuse something that's already out there as a standard. Right? So such IoT fabrics and stacks help you leverage the same stack for multiple applications. And this again helps you sort of span different physical and logical domains, be it sort of a small scale deployment of a sensor within a small building, or something that might work across the entire city scale, or even worldwide. Right? So when you think about such IoT architectures and stacks, so there's been multiple sort of reference designs out there. So this is one from the World Wide Web Consortium. This is the group that actually decides on things like the HTTP protocol and so on. And they have essentially come up with their notion of web of things, right? It sort of goes beyond just the Internet of Things, but sort of the web of things, where they talk more about web-driven applications. So where you have sensors that are connected through device drivers to this kind of a layer over here, which sort of gives you a virtual view of what that sensor is. And then you can use other standards such as JavaScript or JSON to actually push some of these, sort of host some of these things in the cloud as virtual entities. And then you can also have sort of either going directly accessing the sensor or going through other gateway or bridge routers and so on. And then essentially have various APIs that are exposed by these things in the cloud, and you can essentially access these sensors or actuate upon them through these APIs. Rather than directly talk to the sensor, talk to an API that's hosted on the cloud, and then have that API behind the scenes talk to the sensor or the actuator. Right? So this is one kind of a model that W3C has proposed. There are also other reference models from other sort of vendors and providers. So this one is from Amazon's AWS. They had a nice graphic, so I thought I would pull that in. So here again, you have sort of things that are essentially you have applications that come in using your IoT device SDKs. These are sort of APIs exposed by various proprietary vendors. You go through sort of things like authentication and authorization, and the device gateway essentially uses standard protocols like MQTT, WebSockets, and HTTP, some of which you'll hear about later on during the tutorial. And then the data itself might be processed, the stream of information that you get might be processed as messages by things like rules engine or even processing engines and so on. And then you take decisions based on that. So this is effectively your observation and your decision making that takes place over here. Separately, in terms of enactment, you can essentially have this notion of virtual entities or device shadows, where you actually have information about the environment that you're observing, but as a service that you can, that's exposed on the cloud, that you can query and sort of actuate through various applications that you have. Right? So these are a couple of examples of how IoT stacks work. What I will do in the next few slides is actually talk about IoT in action. Right? So the IISc campus itself has been having an IoT project running for about a year or so right now, called the Smart Campus Project, funded by the DAITI, which is the Information Communication Technology Ministry, as well as the Robert Bosch Center over here, where we are trying to sort of prototype a sort of medium scale IoT deployment at the scale of the campus. Right? It's larger than just the scale of a building, but not as big as a smart city, which is hopefully going to come down the pipeline. Right? So I'll just talk to you about how IoT itself has some practical value and how it's deployed in the field, right? So that you can relate some of the abstract notions that you've heard the last half hour with its practical implementation. And one of the goals for us as part of this project is to actually see how you can leverage IoT and big data technologies to make things better on campus, right? Because at the end of the day, the quality of life is what matters, right? So can we improve the quality of life, right? By having this IoT fabric work across campus. And our initial target domain was water management. Right? As we all know, water is a scarce resource, it's the next oil. So who knows, wars are going to be fought a decade from now over access to water. So understanding water consumption within campus, water delivery, water quality, and so on campus, we felt was important, not just for campus, but on a broader scale as you scale out into maybe even a city scale. Right? And as a part of that, we want to get a sense of what are the gaps in technology, what are the technologies available, what are the gaps, and what are the practical issues that you face when you start doing an IoT deployment. And looking at it a bit from the Indian context, right? Because there are unique issues that we deal with over here. So you can't talk about self-driving vehicles over here when you can barely get people to sort of stop at the red light, right? So there are very unique Indian issues that we have to deal with. And there is also issues of the cost and sustainability that's involved, right? You can't go and buy a $1 billion solution for a city when it's not proven in any other sort of environment such as a developing country such as ours, right? So these are the sort of two other goals for us. And what do we mean by smart water management? One of the goals for us is to actually understand how water gets accessed from our local municipalities or BWSSB, and how we actually pump it up to different overhead tanks. If you get a chance to walk around campus, you'll see these huge tanks, right? So that can have about maybe 1 lakh or so cubic liters of water, as well as sort of underground sumps. So these are essentially the buffers on campus where water comes in and are initially pumped up or down. And then from there, they're sort of distributed across various buildings. And how do you actually manage this pumping operation is actually an interesting problem, right? Because if you do it, if you don't do it properly, either you're going to run out of water, or you're going to be having too much water, in which case you've actually over pumped. And pumping operations take energy. So it's not just water that you're wasting, but energy also, or electricity as a part of that. We want to understand if we are delivering safe water. Some of the ISC water networks are decades old, which means that you might have leaks, you might have contamination, and so on. And that's something that we'd like to understand as part of this IoT fabric. And can we also be more aware of our water usage, and as a result, be more sustainable in our water usage, right? So IISc actually has a higher, 3 times more than the global average of water consumption, partly because we have a lot of labs and so on that use water for cooling or for sort of chemistry and so on. But still, we don't have clear visibility in terms of which buildings are taking how much water. And if we did know that, so we'd actually be able to figure out, is this 400 uniformly distributed, or are some buildings more wasteful than others, right? And lastly, can we sort of lower the cost, not just for water consumption, but also for electricity? So these are sort of the broad goals, and these are typically what you would find even if you scale it to a city network, right? So if you want to think about a municipality delivering water to its customers across the entire city, these are going to be similar goals that they have. Instead of sort of large tanks in a campus like this, you'll have large tanks that are in various communities around the city itself. So this gives you a sort of, this sort of the IISc campus map. So if you get a chance, walk around it. So we are somewhere over here. And you have these various overhead tanks spread across campus. And you also have a bunch of underground sumps that are present. And water itself comes from sort of these 4 inlets from within the municipality. And from these 4 inlets, they are pumped up to the overhead tanks and then buffered onto the sumps, and then pumped up to individual buildings in terms of the overhead tanks, right? And we are looking at a campus of about 10,000 people, 50 buildings of very diverse uses, everything from offices to hostels to restaurants to health centers to campus residences. And we use about 40 lakh liters per day of water, which is fairly large. And we use about 10 megawatt of power overall, not just for water pumping. But that again is a lot of energy or electricity bills that we are paying for, right? And this is the environment within which we are working. So we are a mini township, if you want to think of it in that way. And these are sort of various tanks on campus. You can look around if you spot any of them in the next week or so. And these are the underground sumps where the water is buffered also, right? So the goal over here is to see if we can instrument some of these pumps and overhead tanks and get a sense of what the water usage pattern is, and as a result do something meaningful in terms of actuation also, right? So this is our view, this is the IoT stack that we have on campus. So it's actually putting specificity to the earlier abstractions that you saw earlier on. So we have various types of physical sensing, such as water flow meters that actually measure the water flow through big pipes that come in from the municipality and across campus. Water level sensors that actually measure the height of water within a tank or a sump. So you know how much, if you know the sort of these dimensions of the tank, you know how much of water is there. We're also looking at things like crowdsource sensing, where you can use smartphones and get endless people to actually get you data in terms of water quality in, let's say, these water dispensers and so on. And then you essentially have the networking and communication layer, where we are looking at a mix of various communication technologies, some of which you'll actually hear as part of the tutorial later on today and tomorrow, where we're looking at things like Zigbee, sub-gigahertz, Bluetooth Low Energy, 3G, 2G, Wi-Fi. So you name it, there's a mix of these heterogeneous technologies. And we're not doing this just because we can, but you need different solutions for different environments, right? So you've got a lot of wooded area. A wireless sensor network is not going to be very effective, right? So if you've got long distance to cover, right? Zigbee is not going to work. You might need things like sub-gigahertz. So we're looking at, so given our campus is still fairly diverse, we want to actually try out what are the right communication technologies for individual environments, so that when you actually scale out, you are assured that at least these technologies will satisfy a large subset of the real world problems out there. We also look at big data processing, both real-time data processing, looking at archive data processing using things like Hadoop, looking at online analytics or events, looking at machine learning algorithms and so on. And these again, since we have this feedback loop going on, sometimes you might have the luxury of waiting for maybe a few hours or a day to do the analysis and give a feedback, right? But other times you might actually need very low latency. So for example, if you want to control your air conditioning thermostat, right? And you said that, hey, give me the data, I'll process it for 2 days, and 2 days later I'll tell you what the change to the air conditioner is going to be. And that's obviously not going to work, right? Likewise, if you want to sort of control the traffic signals on the street, right? You really need real-time traffic flow information and use that to immediately change the traffic lights. So latency and sort of fast data processing is fairly important. And this is again something that you guys will be learning about in the tutorial. And lastly, you have domain-specific models and analytics, right? So here's where maybe the specialization to individual domains come in. So the sensors oftentimes and the application/analytics are going to be customized to, let's say, the water domain or the power domain or the traffic or you name it, right? But oftentimes everything in between is probably going to be quite general, right? So you're not going to completely change your big data platform just because you go from water to power to traffic, right? So these are more generalized, right? And then you actually have visualization and so on. And here's really where the domain-specific decision-making takes place, right? So where you see that, hey, maybe the water level on this particular tank is low based on these sensor readings. So let me sort of send a signal to the pump saying that, hey, why don't you start pumping water over here? And by the way, the moment you start pumping water, the water level in a different tank, the big overhead tank, is going to go down, which means I have to schedule, next time water comes to the municipality, I have to make sure that this big overhead tank is pumped up first before others. So that's the kind of decision making that happens over here and sort of fed back all the way down here to various kinds of, whether it's to pumps for pumping water, or it might be to human beings saying that, hey, the water quality in this particular dispenser is bad, so go put a notice board over there saying that not to use the water and change the dispenser over there, right? So just to give you a few examples of the different layers over here, this is an example of a water level sensor that we have on one of these underground sumps. So this actually use ultrasonic signals to like a radar kind of thing to measure the depth of the water from the rim of the pump. And based on that, you actually, and if you know the depth of the entire tank also, you sort of calculate the amount of water over here. And not just that, by doing a sampling periodically, you actually get to know the rate of consumption of water as well as rate at which the water comes in to the entire tank itself, right? And this is like a more professional version of this over here, right? We are also looking at flow meters, which essentially are things like these that are attached to your big pipe, and these measure what the rate of flow of water is across these various pipes. This tells you how much water is coming through the various parts of the water network. And these again have different, there are different types, things that you can actually couple around a pipe without actually physically intervening in the pipe, and things where you actually have to cut the pipe and put it in. And again, and sometimes these things cost as much as $1 or $2 per pipe. So we can typically afford to put it only in the main inlets to the municipality, right? And here's where things like crowdsourcing comes in, right? So all these meters, like all these pipes, have an analog meter, right? But an analog meter is not good enough to actually get the data out in a digital form, right? So you can either install a flow meter that costs $1 or $2, right? Or you can think of a solution which actually uses crowdsourcing, right? So some of these meters are by the gate. So when someone comes in through the gate, can they take a picture of the analog meter and do some automatic image recognition and have it converted to digital data that's pushed out there? Now you replaced 1 or 2 lakhs of an instrument with hopefully getting 10 people in a day interested so that they can take pictures of it spread out during the day. And voila, you actually get reasonably periodic data and reasonably high quality data for your application while not having to spend a lot, right? That's where things like crowdsourcing really comes into play, especially in the context of India, where sustainability, financial sustainability is the context. This is another example, and which might be one of the projects that some of you might be working on if you choose to, is one of water quality sensing. And water quality, especially in terms of measuring the chemicals in water, is fairly costly to do automatically, right, using instruments and so on, like physically deployed instruments. But everyone over here who's taken a chemistry lab knows that you can actually have these reagent strips that you dip in water and things change, right? Or like a pH strip, right? And these cost maybe a couple of rupees, right? and you have these kind of strips for different types of chemicals, right? So simple alternative to an instrument that costs tens of thousands of rupees is to actually give out these strips to people. Students on campus, you dip it in water, maybe in the water fountain that you use frequently. The color changes, you take a picture of that, you normalize that against the lighting conditions and so on to see what the chemical level is on the water. And then you sort of push it out in the cloud or wherever, where you take a decision saying that, do I need to notify someone? Is the level bad enough that it has to be sort of taken care of immediately, or are things normal, right? So these and other ideas of crowdsourcing are really relevant in the Indian context, and I encourage you guys to think about that. In terms of communication, we are looking, like I said, at different types of both physical infrastructure networks such as Wi-Fi and 3G, as well as ad hoc networks such as wireless sensor networks. And these are sort of the deployment plan for various wireless sensor networks across campus, so that when you have an underground sump or an overhead tank, and you have water level meters installed on them, they can actually communicate back to the nearest Wi-Fi hotspot. And in order to do that, and since these tanks might be hundreds of feet away from the nearest hotspot, you actually need ad hoc networks to bring them through, right? So these are various network designs that we are looking at in terms of deploying these. And this is an example of one of the modes, which again you'll hear about as part of the tutorial, where it helps you essentially build your own ad hoc network using ZigBee, as well as sub-gigahertz, which is a more like a long-range communication protocol, right? And these are essentially used for communicating data from the sensors to your border gateway. And this is an example of one of the deployments that we have in the ECE building, where you have this overhead tank that's being instrumented with water level sensor that comes through various modes. It jumps across all of them through the peering network, and finally comes to our border gateway, which is a Raspberry Pi, from where you essentially sort of push out data to the cloud for processing, or even do on-the-edge analytics over here. Right? And some of the things that you'll hear about later on this week is also in terms of how do you actually do a network design. Right? Some of you guys might be from an ECE background, where you might actually, all of this might be fairly familiar to you. But the key is that you essentially you have to do a fair bit of on-the-site measurement of signal strengths and so on. And here again, there's a lot of interesting research going on in terms of, can you do that just based on the vegetation cover? So just based on this measurement of the distance between various locations on campus or in a city, as well as the type of, whether it's a building or it's vegetation or it's open roads or so on, can you actually build a model in terms of what the signal strength is going to be without actually going and doing physical measurements, because that's going to be fairly costly and unsustainable. So there's a lot of interesting research to be done over here. And like I said, crowdsourcing is not something restricted just to sensing, but even for communication. Can we actually replace a wireless sensor network to get data from the overhead tank all the way to the nearest building, which might require maybe 10 sensors and maybe each of which costs between 10 modes, which cost between 5,000 to 10,000 rupees each, with, let's say, a Bluetooth low energy sort of broadcasting mechanism that at the base of the overhead tank that just sends out the current set of data that it's collected, and the data jumps onto your smartphone if you've got your Bluetooth turned on, and you use your 3G or Wi-Fi when you have access to it to push data out. So effectively, you've replaced a physical network which you have to maintain with a crowdsourced network that you don't have to really worry too much about. Right? So that's another sort of interesting idea to explore. And lastly, looking at analytics itself in terms of big data processing, we have to look, like I said, not just at the volume of data in terms of Hadoop and MapReduce processing over archive data, but also high velocity data coming in terms of streams, so that you can do real-time analytics and low latency decision making, so that you can actuate back onto the actual IoT deployment. But at the same time, you might want to look at historical data to build models about how do different systems work, so that you can actually build a virtual model of different kinds of behavior patterns, so that you can actually pull out the signal from the noise. Because just because you get a lot of data doesn't mean all of it is useful. You're really looking for the outliers, things that are not normal, that you want to detect. And for this, you need historical data so that you can figure out what's normal and what's abnormal. Right? And clouds are sort of common infrastructure on which you can host some of these big data analytics platforms. But at the same time, since things like Pis are becoming common, Raspberry Pis and Arduinos are becoming common as your border routers, these actually have non-trivial computing power, as do your smartphones for that matter, right? So a lot of the analytics could very well be done on these edge devices without necessarily having to go to the cloud. And looking at how do you mix these two things together becomes fairly interesting. And this is sort of a quick picture of the kind of big data fabric that's deployed for the Smart Campus project. So you have all these modes, these sensors using modes to get data to this Raspberry Pi, which is your bridge border gateway. And from here, sort of things get pushed onto the cloud using a pub/sub protocol. And within there, you actually do things like real-time stream processing using Apache Storm. Part of the data might be archived. Part of it might actually be used to drive real-time decision-making and analytics. And it might be pushed out either as a visualization to a dashboard or decision-making back to the campus environment itself. And these themselves could visualizations or notifications would come back either through your app, which in this case is Android, or your web browser, where you can actually look at how the status of the entire network is. Right, so I've talked about crowdsourcing. So this is what we have managed to do on campus. Again, this is a work in progress. This is a project in progress in terms of using IoT for water, right? And the question, one of the questions for you guys over here, as you learn all these theories and talks during the next 6 days, is to actually think about how these can be put into practice also, right? And for that, we've arranged tutorials on the first, today and tomorrow in the afternoons, after 3:30 or so. And part of the goal for us in this tutorial is to get you to understand what tools, technologies, and standards are out there if you want to start building your own IoT application, right? And these span tools, technologies, and standards for sensors, for communication, for data processing, and for using edge or cloud resources, right? So we're going to try and cover all these layers in the IoT architectural stack so that you have enough raw material to actually put an application together if you want to, right? And besides just teaching you how to sort of integrate all these pieces from first principles, we'll also introduce you to existing integrated platforms for IoT, because some of you guys might say that, hey, I'll do everything from scratch. I'll sort of go buy my own sensor. I'll pick my own protocol, and I'll pick my own big data platform and tie them all together. Some of you might say that, hey, I'm only interested in the application. Just give me a platform that will do all of this for me. So we'll give you a brief introduction to some such integrated platforms that are available also, which might accelerate your time to a solution, right? So both of these are going to get covered. And one thing we're going to do is, given that this is a very fairly diverse space, right? One of the other interesting things about IoT is that it's very interdisciplinary, right? I mean, that's one of the reasons why we do IoT at CDS, because we are part of the interdisciplinary division also, right? So you need people with different skill sets. So it's not just someone with computer science knowledge or with EC knowledge or E knowledge who's going to be able to do that. You actually need people to come together, right? So one thing we are doing for these tutorials, A, because there are a lot of you, and B, because we need to cover a lot of topics also, is to have two separate tracks, right? So you're going to be partitioned into two. And one set of students and participants will go to the sensors and communication track. Another set will go to the software and analytics track, right? And the goal is to essentially bring you back together, right? To actually do something as a team, right? So for people with maybe ECE or E background might choose to go to the sensors and communication track, and people with a CS or IT background might choose to go to the software and analytics track, or the other way around if you choose to, right? It's really your call, right? So following these two tutorials of about 3 hours each today and tomorrow, we're going to open up the entire sort of school for a hackathon that's going to be running for the entire week, right? Literally starting from today afternoon, right? And the goal is for you to form teams, preferably 2 from the sensing and communication track, 2 from the software and analytics track, form teams of 4, and pick an interesting IoT application to come up with and actually implement it, potentially from first principles. And for this, we'll give you a standard set of sensors. There's going to be a sort of literally an inventory of sensors we'll give you, so you can look at those sensors, figure out which ones you want, and see what kind of applications you can design using that. And we'll give each of these teams a Raspberry Pi also, so that you actually have something as a bridge gateway. And hopefully you'll be able to get some of you some wireless sensing modes if you want to do ad hoc sensing networks. If you guys have smartphones and laptops, you can use those. We'll give you a virtual machine on the cloud. So we'll try to give you the basic building blocks and the training to use them for putting together an IoT application. And we leave it to your creativity to come up with cool ideas for IoT applications that you can put together. And on Saturday, we'll actually have a demonstration of the outcomes for various teams. You'll be giving us a presentation, and we'll choose which ones are really top-notch, right? So you'll be competing amongst yourself also as a result of that. We'll also have mentors to help you out if you run into any specific questions. We'll have a mailing list, which I'll sort of show in the next few slides, where you can ask questions. And we have a team of very enthusiastic students here at CDS and from ECE who will try and answer your questions, besides also leading the various tutorials. Right? So in terms of the schedule for the tutorial today and tomorrow, so today it's going to run from 3 to 6:30, and the schedule says 6. We're going to try and push it a little bit later till 6:30. So by the way, this is going to be a very, it's not just active learning, but it's also going to be an intense learning that you're going to have over the next 6 days. So which means that some of you guys, if you really are thrilled about it, and if you want to, you might be up late till 10 o'clock, 11 o'clock every day of the week participating in this hackathon. So it's really up to you in terms of how much you want to engage and how much you want to take away as part of this school, right? So as part of this today's tutorial in the sensing and communication track, first we'll start up with a join session in terms of what the tutorial itself will cover in more fine detail than what I'm giving you right now. And then Ashish is going to talk to you about how do you actually pick sensors, what are the different types of sensors, how do you actually read data sheets for sensors, understand how they work, how do you interface them with ADC controllers, what protocols to follow, and so on. And how do you actually get the data from the sensors onto your Raspberry Pi or through your Mote, both directly or through things like Contiki. And these are going to be hands-on also. So hopefully at the end of this session, you would actually play around with a few sensors and maybe a Pi or a Contiki Mote or so on, and be able to get data out of that you can read and take it forward. We'll have a brief session on Android and Bluetooth low energy based on a project that has taken place earlier on, just so that you have some context in terms of smartphones also acting as the edge. We'll have a couple of talks on specialized devices for energy monitoring. So one of which is called Joule Jotter from within IAC that came from T. Prabhakar's lab here, and another called JPlug, which is available commercially, that can be used for smart energy metering so that you can real-time data about energy loads and so on. And we'll have Tanuja from DataGlen also talk about pre-canned kits for IoT, which you can go and purchase if you choose to later on, which give you a set of breadboards and sensors and so on, and integrated with the IoT backend platform from DataGlen to actually play around with. And lastly, we'll have both the sensing and communication track as well as the software analytics track come back together at the end of today's tutorial to actually start forming teams, because we want you to get started with forming teams. So at the end of today's tutorial, hopefully you'll have enough information that you can actually start matchmaking amongst yourself and start thinking about project ideas in terms of what you want to, and we'll be here to answer questions in terms of what resources are available for you. And following that, again, tomorrow afternoon, you'll have another tutorial so that we go through, so give each of you guys Pis and access to Azure VMs. And this, again, will be a joint session in at 3:30 or so across both the tracks. And you guys your teams will get to know how to access the Pi, how to access the Azure resources, so that you can get started with your projects themselves. So we'll break out again for the wireless networking and communication talks, where you'll hear about various types of internet protocols, IPv6, RPL protocols using CoAP and MQTT, which are again IETF and OASIS protocols for transferring data, things about wireless sensor networks, 6LoWPAN. There's a bunch of interesting standardization going on to support IoT specifically, right? And you'll hear a lot about that. And hopefully you guys will also be able to put together a small wireless sensor network so that you can pull data from the sensor, which you heard about today, and actually get it onto the Pi using a wireless sensor network as part of your hands-on session. So that's for the sensing and communication track. And the software and analytics track, which is going to be the other half of you, again, we'll start with the joint session. And then you'll essentially get a quick overview of accessing the GitHub. And a lot of these things are actually posted on GitHub. I'll get to that in the next slide or so. And then you'll hear about various IoT fabrics, software fabrics that are out there, and how event-based architectures are critical for some of the low latency and streaming processing that's necessary for IoT. Here you'll hear about pub/sub protocols such as MQTT, data formats and representations such as SendML, so that when you send a temperature information from point A to point B, the recipient actually knows its temperature data and what the units are and so on, without you actually having to invent your own sort of custom standards. We'll talk about complex event processing, where you can actually look for patterns in events that you're receiving, so that if you want to look for, let's say, water level suddenly dropping from a level of maybe 100 centimeters to 80 centimeters within a very short period of time, that effectively is a pattern you're detecting from a series of events. And that might essentially tell you maybe someone turned on the tap and forgot to turn it off, right? So these are interesting patterns that can help you decide and take action, right? So CEP engines help you with that. And again, the end of today, you guys will join with the sensing team to form teams. And tomorrow for the software analytics, again, once you have the join session in terms of using the Pi and Azure, we'll talk about stream processing or distributed stream processing, where you can actually compose building blocks. Because typically, if you want to process data and take decisions, you might have to do some data cleaning, data parsing, you might have to do some data aggregation, you might have to look for patterns beyond that, you might have to sort of do denoising and so on, you might look for predictions and trends to see how let's say the water level is going to be 2 hours from now. So all of this requires you to compose various building blocks together, and things like stream processing engines help you compose various building blocks together. And we'll talk about Apache Storm, which is a sort of fast data processing platform on the cloud for this. And we'll also briefly talk about using the edge device, your smartphone itself, if you guys have an Android phone, in terms of using it as a platform for collecting data and sort of publishing it to the cloud, and so on. We'll have a sort of catch-all session in terms of analytics and visualization. So we'll briefly take you through using R, using Beca machine learning library, using Rickshaw for visualization, and so on. So hopefully at the end of all of, and lastly, we'll talk about the DataGlen IoT platform, which sort of tries to combine all of these things into a pre-canned, the proprietary platform that you can use out of the box, right? So this is going to be your schedule for day 2 for the software and analytics track, right? So let me maybe pause for a moment and take any questions if you have at this point in time. Okay, so I seem to have saturated you guys. So how many of you are connected to the internet right now through the IISc campus network? Sorry? You're waiting for it. Okay, so here it is, right? I wasn't sure if it went out as part of your registration packet. If not, make a note of this. We'll make sure this is written outside in the whiteboard also, in case you don't have a pen and paper handy. So try this out, meaning I haven't tested it out this morning because this is a guest Wi-Fi account that's been set up. So if you run into any trouble, catch me, or we seem to have Rajrup and Ravi back there. So you guys want to raise your hands? Okay, so they are all volunteers from CDS. So if you have any questions on getting access to Wi-Fi or any sort of technology related matter, you can have a word with either of them, and they'll help you with this, right? And as is obvious, this is a campus network, which means make sure you use it fairly, reasonably. Don't do things that you shouldn't be doing. Okay, so I'll leave it at that. And there are a couple of things, action items on you, right? And this is something that we'd like you to start doing in preparation for the tutorial, hopefully by lunchtime or so, or over lunch, okay? So one is we're going to have, we've set up a Google group, essentially a mailing list, for all participants, especially to sort of answer questions on the hackathon and tutorial and so on, right? So make sure to subscribe to this. So just go to this link and essentially say subscribe, and Rajrup will get a request for subscription and he'll approve you guys immediately, okay? And second, get connected to Wi-Fi here at IISc, which I gave you the SSID. If it doesn't work, talk to me, we'll fix it. Third, if you have a laptop, and I'm hoping many of you do, try to get a Git client installed on it, as well as an SSH client. And those who are in the software and analytics track, make sure you have some kind of a Java developing environment such as Eclipse or so on installed, JDK. So by the way, all of this is actually listed online, so at the link over here, so you don't have to memorize it. This is just as a recap, so that you can look through what's online and do things on your own. And if you choose to, you can also sort of install some of these additional optional stack, so that it will help you guys both during the tutorial as well as through the rest of the hackathon. And for the sensing and communication track, there are some dependencies on Ubuntu OS if you actually want to interface directly with your laptop. If not, the Pi is always there. If so, an Ubuntu OS is preferred. And if you don't have it installed, don't freak out about it. We don't want you to be reimaging your partition right now. So just install maybe a virtual hypervisor or something like that, like VMware or Zen, and just install a VM image of Ubuntu. That should be fine, right? Lastly, everything that you're going to be going through in the tutorial are hosted on GitHub. So this is one thing that you might want to remember, github.com/dreamlab, which is the lab I head, /IoT school, or just search for GitHub and Dreamlab, and that will get you to the link. And everything that you're going to be listening or hearing in the tutorial, including slides, codes, documents, URLs, as well as all these slides, are available in this location, right? So this is really the only starting point, as well as internet connection and laptop that you need to get all this information. So try to get all of this done by lunchtime. And within here, you have something called the common folder. Let me see if I can actually pull it up quickly. All right, this is really where we are. Right? So common is really where all the stuff that we are providing you guys is going to be over there, which means that those who are familiar with Git, if not just to get a quick crash course online, you just need to go and sort of clone this entire folder onto your local laptop and keep syncing it periodically in case we keep updating it. So this has everything what you'll be learning in the sensing track, the communication, the analytics and big data, the slides that we're going to be presenting. All of that is over here, including things like setup for connecting to the IIC network and so on, is all posted over here, right? So clone this to your local laptop and keep it handy, right? The second is this folder over here. And here is where all the cool stuff that you guys are going to be doing for the rest of the week is going to be posted. Right now it's empty because it's going to start getting filled once you start forming teams. So once you start forming teams, create a folder for your team with your team name. And as you develop scripts and software and so on, start pushing it over here, right? Including your final slides for the presentation. So we want to make sure that whatever you guys build is not just available in this hackathon or for this summer school, but it's available in the public domain for anyone out there to come and use, which means that you guys are actually going to be building a repository of really interesting IoT applications for the rest of the world to start using, okay? All right, so I'm almost to the end of my slides. So some other things for you guys to do tomorrow and later. So form a team by hopefully end of today, and drop us a note with your team name. Create a folder in Git under the Teams folder with your team name and a list of members that you have so that we know who are the teams and how we can reach you. And by tomorrow morning, we'll also give each of your teams a Raspberry Pi, which you can set up and install, and also access to one Azure VM where you can host things on the cloud and run things like event processing engines or stream processing and so on, right? And by the end of tomorrow, you guys should have finalized your project topic, right? And that way we'll know whether we have all the right sensors for you, and we'll also try to assign you to a mentor so that you can sort of work with a mentor through the rest of the week as you start working in your hackathon, all right? Any questions before we wrap up this session? So right. So the question was, the comment was that a lot of you guys are interested in both sessions. But honestly speaking, IoT is so broad, right? So for example, the water management project, which it seems fairly small. It actually has 6 different faculty working on it. And each faculty has about 3 students. So you're looking at about 15 or a team of 20 for looking at a single application from 4 different departments, right? So IoT is intentionally interdisciplinary, which means that you have to sort of assume that a single person does not know everything, right? So we are actually forcing you to go through these 2 sessions so that you learn to come together as teams and talk to each other, not talk across each other. Okay? Satish, are we recording everything? Right, so, but 202 doesn't have the recording set up, right? So it would only be over here. Right. But all the material that we're using, code, script, slides, references, everything is online, right? And if it's not online right now, it will be by the end of the tutorials themselves, right? So resources are there online. So we had another question? Yes, so we already have the data sheets for the sensors online. So we just need to do a sanity check to make sure all of them are working and in sort of ready process. So today during the tutorial, the last session for today, we'll actually walk you through some of the sensors that are available so that you can help design your sort of project around that. So that will be covered as part of the tutorial. No, that's not going to be possible because we actually want you to be working on your sort of projects on day 3, 4, and 5, and maybe a bit of 6, right? So, so hopefully you'll be spending 3 to 4 hours after all these lectures working on your project, or maybe before the lectures start. So we want to set aside time for that, and don't want to repeat the session. But all the material is going to be available online. Okay, so we'll wrap up with that, and Satish.